I'm Matthijs. I'm a PhD student at the Mullard Space Science Lab, working with Marta and Jason on developing basically deep learning techniques for image reconstruction in interferometric imaging, focusing on like astronomical applications, and especially with the like increasing amount of data that needs to be processed in, for instance, radio telescopes. We are really looking for reconstruction methods that are more computationally efficient than the conventional approaches in order to deal with these huge amounts of data. That's basically what is driving this research. So I'll start with explaining like what is interferometric imaging, because I'm sure some people might like a refresher, and then I'll discuss like what is actually the problem and where are the challenges. Then I'll explain the learned image reconstruction approaches that we developed and that we used, and then show how we apply this to two different cases. The first case is an optical telescope. It's an interferometer, it's called SPIDER. And the second case would just be to apply this to radio telescopes. So first, interferometric imaging is different than your usual kind of telescope. So instead of having one dish that collects light and focuses that as an image on your detector, we have actually multiple telescopes or antenna that measure the interference signal of your source. So if you want to kind of explain that more visually, if we have an image, as you can see on the left here, what a interferometric telescope does is it measures points of the Fourier transform of the image. So if you take the Fourier transform of the image, you can represent that as the amplitude of the Fourier signal and the phase of the signal, because they are complex valued. And in this representation, you have features at low spatial frequencies, and these basically define the global profile of the picture. And then you have features at large spatial frequencies, and these actually detail the small variations in the image. And what happens in interferometric imaging is that we have two telescopes or antenna that form together what we call a baseline. And this baseline is sensitive to one specific frequency, spatial frequency in this case. And what they do is they measure what we call visibility, which is basically just one Fourier measurement of the image. So here on the right, you can see an example of what a visibility coverage looks like for a radio telescope. And this is just basically all the points of the Fourier space that it samples. So every point on the image on the right is one measurement. So one new interesting way of applying this is this telescope called SPIDER, or the segmented planar imaging detector for electro-optical reconnaissance. And this is a new concept design for a space telescope, which is developed by UC Davis and Lockheed Martin. And the idea is that they are building what they call photonic integrated circuits. But basically, it's just a large chip with on it several lenses. And these lenses all capture some light. And then in the chip, they combine those into interferometric measurements. So basically, each one of these chips is one 1D interferometer, and by placing a number of them in a disk, they get like a full 2D coverage. And the idea is that instead of using very large space telescopes, which have traditionally one primary mirror and then a secondary mirror to focus the light, you can basically shrink this down to a 2D disk. And by doing so, you can reduce the weight and therefore also the cost of making space telescopes. So for SPIDER, there are a few challenges in doing image reconstruction. In the top right, you can see the arrangement of the lens slits, on the device, and that results in a coverage that looks like this. So these are all the Fourier measurements that it samples from the Fourier plane. So one of the challenges for SPIDER is that we don't have a lot of measurements, so it's actually quite sparse, with about 4,000 measurements. And because the measurements are so structured, they are very periodically arranged in a way. This actually causes quite a lot of aliasing problems when you're trying to reconstruct the image. And then the third challenge kind of for SPIDER is that what we want to do is we want to design methods that can also be used for real-time reconstruction, which can be especially interesting if you want to do Earth observation kind of things. So in order to do this, we have to design methods that are very computationally efficient. On the other hand, we have radio telescopes where we don't have a small amount of measurements, but typically have a huge amount of measurements. For instance, for SKA, well, SKA low has already 130,000 antenna, so that doesn't even say how many visibilities are. And these telescopes produce like terabytes of data every second. So there's huge challenges in trying to deal with these huge amounts of data in an efficient way. So as I said, we have a large amount of visibilities, which can be a problem. But one other interesting thing is that the visibility coverage of a radio telescope depends basically on the observation. So whereas for the SPIDER telescope, you would point the telescope in the direction of your source, with telescopes that are based on Earth, we cannot really point them towards the source because we have to rotate the Earth. So instead, what you basically get is that your configuration is projected to where the source is basically on the sky. So that's one thing. So depending on where your source is on the sky, your visibility coverage changes, but also these observations typically go on for hours, so that what they actually do is they use the rotation of the Earth to change the configuration slightly, just by rotation. And you can see that in the visibility coverage on the right, like all these trails are basically one baseline that is being changed because the Earth rotates. And in doing so, they can gather much more measurements and get a more complete coverage of the UV plane. But this also means that if you want to design any kind of learned reconstruction methods, then we also need to make sure that these methods are robust to changes in the visibility coverage, which can be a challenge. So to summarize this kind of problem into one thing, we can describe it in a very simple formula. So if we have some kind of image X, and we have some kind of Fourier measurements that are not uniformly distributed in the Fourier plane, which we call Y, and we have some kind of measurement operator that maps from these images to the measurements. And then, of course, we also have some noise. Now, the problem is that we don't want the Fourier measurements, but we want a nice image to look at. So in order to get that, we need to find the operation that inverts this operation, which can be quite difficult. And it's difficult, one, because there is this noise component added to this process. So it's not as easy as just getting the inverse of this measurement operator, which basically simulates the acquisition process. So that makes it difficult. But the second difficulty is that since the Fourier space is only sampled at non-uniform points and there's large gaps in the Fourier space, it's actually not trivial to just invert this. So one kind of way of solving this, which is kind of the classical approach, is to use things like variational regularization, where we set up an objective function and try to find a solution that satisfies this. And typically, an objective function like that has a part which is a data fidelity term and some kind of regularizer, which represents the prior information. So in astronomical interferometry, we typically use an L2 norm, on basically the measurements. So if we generate an image X, and we apply the measurement operator to it to get some kind of measurements, we compare those to the actual measurements, and if the distance is small, then we have an image that fits our measurements well. But this problem is actually degenerate, so you need some kind of prior information. So in this case, we use a dictionary of wavelet bases, and we know that the image is typically sparse in those bases. So we can use that as prior information. The problem with these kind of methods is that they are iterative methods, and at each iteration of the optimization, it has to evaluate the measurement process. And this can be quite costly, especially if the number of visibilities is very large. So these methods, while they work very well, they can't really be used to reconstruct things very fast. So this is where kind of the learned image reconstruction can come in. So what we want to do is we want to use deep learning to solve inverse problems. And we want to do this because we want to get rid of the mathematical priors that are not specifically designed for a problem and maybe are not super informative, and instead use data-driven priors, which are based on training data. So if you have a very good data set that represents your data well, you can use this as a prior, and that actually will lead to a higher reconstruction quality. And then the second thing is that we want to find methods that don't need to iteratively apply this measurement operator, so that we can get a better computational efficiency. So there are a few different reconstruction approaches. So the first one I'll discuss is learned regularization. So this is very similar to the classical approaches, but instead of using a mathematical prior, you can basically learn a regularizer and use a data-driven prior in this way. The problem is that while these methods give you very high reconstruction quality, they still need some kind of iterative optimization, so they are still computationally quite costly. On the other hand, you can do something like a learned sequential model, where you use the pseudo-inverse of the measurement process to do kind of the heavy lifting, and you combine that with a pre-processing network, which kind of cleans the measurements. Then you apply your pseudo-inverse to get images from those, and then you can use a post-processing network to clean those images into a final reconstruction. These methods are very fast because they only have to evaluate the measurement process once, but then they are also limited by how much information is captured in that one application of the measurement process. And then finally, there are some kind of hybrid approaches where you unroll you kind of unroll an algorithm, and these basically use both learned parts and model-based parts. So you can see this as a learned. The easy way to look at this, if you have, for instance, a learned gradient descent approach, you can unroll a certain amount of application iterations, and at each iteration you calculate the gradient and then learn how to update the image to improve on reconstruction. And then if you unroll that for 2 iterations, you have basically those 2 blocks and learn them as one end-to-end network. And while these methods are very, they can give you very high reconstruction quality, and depending on how many iterations you unroll, they can also be quite computationally efficient. It depends, but they are really good. So for our approach, we started with this learned post-processing approach, where we basically have the measurements and then use our telescope model to create our initial dirty image, which doesn't look great. And then we use a neural network to do some post-processing to get our clean reconstruction. And how we implemented this was using what we call a UNet, which are typically networks used for biomedical segmentation problems. They have also been shown to work very well for denoising problems. So the input to this network will be one image, which is your dirty image. And then the nice thing is that the UNet does denoising at different resolution scales. So every time you go down in this U, you downsample by a factor of 2. So you get a smaller image size. And then here you go back up again. And then as an addition to this, we wanted to implement a learned unrolled approach. So still we have the measurements and use the telescope model to create our initial dirty image and use that as an input to our neural network. But then inside the neural network, we actually use the telescope model and the original measurements to provide gradient-based updates to our network to improve the reconstruction quality. So what that kind of looks like is this. So we still have the same UNet structure, but at several points in the network, what we actually do is we take the image and then we calculate the gradient, which is based on the loss function, to basically perform a learned gradient update at several steps of the network. And the nice thing about implementing it in this neural network architecture like this is that only at the first scale, we apply this measurement on the full size image. But on the smaller scales, when you go down in image size, these operators actually get much more efficient because we're applying them to lower resolution images, which means that they are also not as computationally costly. So basically the computation time is dominated by the operations on the full scale. But if we go down in image size, that also means that for these gradients, we need to subsample the measurements. So instead of using the full Fourier domain on the first scale, if we go down in scale, we actually only use part of the Fourier domain. So let's see how we actually use this for Spider and what kind of results you can get with this. So for Spider, we did both reconstruction of like galaxy images and satellite images, so like Earth observation kind of tasks. So what you see here are some satellite images. On the left, you can see the true image. And then you can see what we call, well, which is the pseudo-invert, which is the dirty image. Then there is a primal dual reconstruction, which is a classical optimization technique, which is iterative. And then you see our learned post-processing, which is the UNet, and the learned iterative method, the gradient UNet. And you can see that the UNet and gradient UNet do a really good job of recovering an image which looked quite similar to the original image. And the gradient UNet is a bit better at getting some clear edges and just a bit higher quality reconstruction. You can also see the peak signal to noise ratio, which is a metric for image reconstruction quality, with a higher value being better. But while the reconstruction quality is really good, and that's very interesting, it's more interesting to look at how efficient these methods are. So if you have an iterative method, you can have an iterative method with like 300 iterations. That means you have to do 600 evaluations of your measurement process. And that means that they are quite slow. Whereas if you use the UNet, we only have to do one evaluation of the measurement operator. So these methods are a lot faster. And in our implementation of the gradient UNet, which is our learned unrolled iterative method, we actually only use 11 full-scale operator evaluations, and all the other evaluations are at reduced image scales, and those basically don't contribute a lot to the computation time. And in doing so, we actually achieve like in the order of tens of milliseconds of reconstruction speeds, which really opens up the possibility of doing like real-time imaging with Spider for the first time. Then the second part is to see if we can adapt these methods to be used on radio telescopes. So just to remind you, one of the challenges for radio was that the visibility coverage is different for every observation because it depends on the pointing and the Earth's rotation and stuff. So in order to kind of find methods that work very well for any kind of visibility coverage, we designed a few different approaches to test this. So the first one would be a true coverage. So this is actually, you know beforehand what the coverage will be, and you train the model fully, which is the best thing you can do, and which is what we call like the oracle or a benchmark. Then the second approach is to have, like, you train your model on a single coverage, which is not the actual true one because you don't know it yet. And then at the end, you don't change any of the weights, but you just switch out the visibility coverage for the actual one and use that for evaluation. And then the third approach would be to use a distribution of coverages, where we actually create data using different visibility coverages and then use that to train a network. And then at the end, you change, you don't change the weight, but you just change out the measurement operator for the correct one and use that for evaluation. So using these methods is really nice because theoretically you don't need any retraining to for every observation. Whereas if you want to train on the true coverage, you would have to retrain the method every time. So the question is, how well do they do? And as an addition to this, we wanted to have some kind of hybrid approach, which is where we use transfer learning. So we take these first two cases and then we fine-tune them for a short amount of time using the actual true data to see if that improves the performance. So if we just look at how long it takes to train these networks, we see that if you want to train something fully, it takes about 30 hours for the UNet and 50 hours for the gradient UNet, which is just too long. If you need to train a network for 50 hours for every, I don't know, 8-hour observation, it's just not viable. So it's better to use these methods that either don't use any retraining at all, or that use just a small amount of retraining for every observation. But then the question is, how well do these perform? So first we'll have a look at how the UNet actually performs. So on the left, you can see the distribution of reconstruction quality, where we train on the true coverage, and you can see the PSNR, so higher is better. And what you actually see is if you train a UNet on data from a different visibility coverage, it actually performs very poorly, which makes sense because these UNets are post-processing networks. So basically it learns how to correct the specific artifacts that are in your image. But if you change out the visibility coverage, then the artifacts will look different. So the network will not have learned how to deal with that. And we can see that actually using a distribution of coverages works a bit better because it has seen more of them. It knows kind of generally how to correct for them. But we also see that if you use some kind of transfer learning, that actually improves the quality quite a bit. But what is more interesting is that if we look at the gradient UNet, we see that these perform much better. And that's because they have this measurement operator embedded in the network. So we can actually see that now it actually works very well. If we just train on a different one and then swap it at the end, it doesn't really matter a lot. And also, if we fine-tune the models at the end, we actually see that we get very similar performance to the true coverage. And the nice thing is that we still get this at this at the same speed as we had before. So these images or these networks were originally trained on these simulated galaxy images, which, if you look at the reconstruction, so this is the true image, then the dirty image, and the oracle, and then the 4 different approaches. You see that they look very similar, but the peak signal to noise ratio is quite different. But to get a more representative example of what the reconstruction quality looked like is we applied this to a out of sample radio data, some actual radio data, and this is on a logarithmic scale. And here you can see that the gradient UNet actually performs very well. And training on a single coverage, you get a good reconstruction quality, which is very similar to fully training the model, but only with a very short amount of retraining, you get basically the same performance. And this is basically the first time that for radio interferometry, we have learned these end-to-end networks that are robust to changes in the varying measurement operators, which is very cool. So yeah, just to conclude, the methods we developed can really accelerate like the imaging pipeline and just speed up reconstruction a lot, and also give you superior reconstruction quality because we include the measurement operator inside the model. And we've also shown that this can actually be used for radio interferometry, where the visibility coverage can change from time to time. So this is really the beginning of trying to implement these methods for the large radio telescopes. Cool. That's it. Are there any questions?